welcome to the Solar Congress 50. This is session 4. You've been with us for quite a few minutes now. Thank you for staying on. I think, yeah, we are about ready to start. I see a few more people are still joining, but they can catch up. That's fine. We are very pleased to have all of you here. This is our second day of Solar Congress 50, and I'm very happy to kick the second day off with you now. My name is Arabella. I am the Communications and Outreach Officer here at the ISES HQ in Freiburg, Germany, and it is now my great pleasure to introduce you to our session introducer for today, Fred Morse. Fred is joining us over the phone. So Fred became first involved in the renewable energy issues related in the late 1960s when he served as Executive Director of the White House Assessment of Solar Energy as a National Energy Resource. And Fred has been a trusted ISES board member for many years, and he has greatly supported the SWC50 in coming together ever since the idea of this event was born several years ago. So Fred, I'm now happy to hand over to you. Thank you.
Arabella, thank you. Thank you very much, and good morning, good evening, good afternoon to everyone who's here. For the past 60 years, the members of ISES have undertaken research, product development, and advocacy for the growth of solar and renewable energies. And this meeting is a celebration. It's not a technical conference. It's a celebration of what's been achieved by all of you over the past 50 years, and a discussion of what needs to happen in the next 50. And let me tell you, I think it's going to be a lot sooner than the next 50, I would say, an emphasis on the next 10 years. Through this conference and the related ongoing online museum and booklet, ISES aims to provide resources to help us all accelerate the transformation to a 100% renewable energy world. Let me comment on those two words, booklet and museum. The booklet is a compendium of solar pioneers, people and companies that have played a key role in this evolution that we're all celebrating. And the online museum is an incredible opportunity to allow you to walk through the history and the evolution of solar energy. And in particular, for example, you could take a tour through the world, the evolution of solar heating and cooling on that virtual museum. We'd like to thank our partners, and Arabella will put there it is. We'd like to thank our partners, our platinum partners, GSES from Australia and NREL from the USA, and our gold partners, Smart Energy of Turkey, and our 20 sponsors who are listed in the booklet that I just mentioned and who appear in the museum. Please note that recordings of this session will be available at the end of the conference. And this session, as all the sessions in this conference, address important aspects of energy transformation. And this session in particular, the transformation that has happened and must happen in the heating and cooling sector. It's easy to forget the heating and cooling sector with all the excitement about PV and wind, but one should never do that. There's too much energy there. Our session moderator is Professor Andreas Häberle. Andreas is a director of the Institute for Solar Technology, SPF, at ISES, Switzerland. He's a physicist from the Technical University of Munich, and he's earned his PhD at the Fraunhofer Institute for Solar Energy Systems in Freiburg, Germany, in the field of concentrating solar thermal power. The institute that he directs has been a driving force in research and development in innovative energy technologies for more than 30 years, focusing on energy efficiency and renewables in general, as well as solar thermal and solar electrical energy in particular. So Andres, before I fall asleep, I've been up for 24 hours. Let me introduce, I've introduced you. Let me transfer this session over to you.
Okay, thank you very much, Fred, for this kind introduction. It's late for you, it's early for me. Good morning, everybody. As you said, solar thermal is the topic for our session now. Heat is easily forgotten. Solar thermal is easily forgotten, but heat makes up for half of our energy consumption, so it must not be forgotten. This session will especially focus on solar thermal and other technologies to meet the heating requirements of industry, of communities and buildings. We have 5 stakeholders, and I will try to moderate this session. The rules are we have short presentations, up to 10 minutes. If you exceed the 10 minutes, I'll probably interrupt you. I don't think that will happen, but just to be warned. And then we will follow with a Q&A session, extended Q&As, so all of you have the opportunity to ask questions. Please write them in the chat. I will read them out then. Please direct your question to one of the speakers, to one of the panelists, so we can address the question properly. And yes, feel free to write your question. We will address all of them in the Q&A after the 5 presentations. We'll continue with Stephen Meyers. Stephen served as the ISES Executive Committee from 16 to 19, heading the ISES Infographics and Working Group. Steve is a mechanical engineer with a PhD in solar and renewable low carbon heating. He holds a global expertise in solar energy, energy efficiency, quantitative research, and now he is Vice President of Engineering at Oishi. Some of you might not know it. That's a company working on vertical farming, vertical indoor farming. Quite fascinating. But the topic Stephen is talking about is solar heat for industry. And I'm looking forward to your presentation now, Steve.
Thank you for the intro, Andreas. Thank you, Arabella and Fred and everybody else to allow me to give this presentation. So I'm going to spend a few minutes now to discussing how solar heating can really help out within the industrial process sector. So right now we have a picture of the Hut-Brauerei, or the brewery, here in Kassel, Germany, where I did my dissertation. Here there is a good-sized project which solar process heat is used to preheat the water during the brewing process, and it's always a good thing to combine solar energy and stuff like that, along with a way to have fun after a day of work. So there is a way to combine work and pleasure at the same time. So first, I'd like to also introduce the infographics that ISES has produced. The most recent one right now has focused on solar process heat. For example, there is an example for the metal manufacturing sector in Chile. There is like I said before, there is a beer brewing example in Germany. And finally, there is a solar process steam generation plant that has been installed in Jordan for the pharmaceutical industry and the manufacturing of medicine. So please go ahead to the website below, have a look at these infographics, and please share them with your professional networks to provide an easy to understand way about how solar heat can really help out to produce the things that we use in our everyday life. So first I want to go into why solar heat for industrial processes. Well, as Andreas previously discussed, a very large fraction of the global energy use throughout the world is used for process heat. About 1/3 of the global energy use is actually used for within the industrial sector, from which 3/4 is actually used for heating, which is quite so surprising. People often think that electricity is the main demand, but in reality, 3 times more heat is needed for manufacturing and production of goods than electricity is. So within this 75%, if we look here over on the right-hand side, is a split up of the 3 main buckets of heat demand. We have lower temperature heat, which is what we define as below 150 degrees Celsius. This is really what you would see in the food and beverage sector and in typical things that you would buy in the supermarket, things like that. Anything that requires boiling or cleaning, or drying, this would be considered low temperature heat. And this is currently now the main focus of the solar heat for industrial process market, because that's really where the current collector technology, this is more the sweet spot of where SHIP can really play a big role. Moving up the temperature chain up to 400 degrees Celsius, this is the start of a larger scale type manufacturing like oil refining, stuff like that. Then you go into the high temperature heat, and this is really where you get into steel and raw metal formation, as well with concrete. So current technologies, this is rather challenging, but in the future of solar heat for industrial processes, this is where we will go to. Excuse me. Sorry. So before we go further, from the current projects that have been built throughout the world, there's a very good website called ship-plants.info, which I'll share a link later. But from this website, it's a great collection of different plants that have been built throughout the world. And the most popular application used for solar heat for industrial processes is within the food and beverage sector. So moving forward, so how exactly does solar heat for industrial processes work? So on the upper side here, we have a simple flow diagram going from left to right. So for industrial processes, the temperature that is required is extremely important. You need to heat a certain product to a certain temperature in order to cook it or prepare it for its next processing step. So within the solar collector, the loop is always run at the higher temperature to make sure that the temperature that it can produce is quite similar to the temperature that the process demands. Once this temperature is achieved, it is sent to a charging loop to charge a storage. And in this case, this will be a very steep thermocline in order to guarantee very hot temperature, right at the top to prepare for the process, while the bottom is cold returning fluid from the used process. And then finally, the process load, which can vary both in temperature. Some processes can be 50 degrees Celsius, but some can be well over 100 degrees and upwards up to 150 for steam or pressurized hot water applications. But also what's quite unique in the process heat space is the load demand. And this is really quite process dependent, where if you have a daily operation that operates between 95, you'll have a big daytime peak. Whereas in some more industrial settings, you will have a large peak at nighttime actually to prepare a heated bath for a metal plating process. So this is more the unique aspects when we speak about solar heat for industrial processes, is meeting this new sort of heating demand with a resource that is only available during the daytime, hence the need for the storage. So where do we start with solar heat for industrial processes? Well, the first biggest adopter was the agricultural manufacturing sector, and in particular crop drying. This was a very easy use case. The timing of the greatest solar radiation along with the timing of the crop availability happened at the same time. And the use of an air collector, which is not the most popular collector choice right now, but it was the easiest path forward to preheat the air just a little bit more to accelerate the drying process, to really make the product dry faster and make it available for market quicker. So here we have a picture of a solar air collector system installed in Argentina. This is back in 1980, so about 40 years ago now. And this was made to accelerate the drying of tobacco, which was hung up in the channelway or in the facility behind the solar collectors here. And this project was and one that was built next door to was almost a half a megawatt thermal, which is quite large, but really one of the largest first adopters for solar thermal or solar heat for industrial processes. Moving forward, although this is in 2008, it was still in the earlier years of industrial process heat. This is a great example of a parabolic trough collector for actually making processed steam, which was used in a food processing facility over in the Central Valley of California, which is where the vast majority of agriculture is done for the United States. And this steam was used to heat up frying oil to make potato chips. And this was also quite a large project of around 5,000 square meters of collector space. So where are we right now for solar heat for industrial processes? Well, from where I view things, I think a lot of great work has been done over the past couple of decades to really perfect the technology, make it quite efficient, and really make things really robust and reliable so that you are guaranteed heat when you need it. So the next step within the sector are three main things. The first is to really figure out what are some of the best business models to accelerate the advancement of solar heat for industrial processes. It is quite challenging. It is a capital intensive venture. And so people are coming up with unique ways to spread out the financing load and to provide incentives to accelerate the technology and its adoption. Furthermore, over with my colleagues or with my friends at NREL, the National Renewable Energy Laboratory, a lot of good research is going into a county by county assessment of one of the world's largest economies to best understand where process heat is available throughout the US, then also how good is the solar resource in these different areas and how best can process heat be met with the application of solar energy, with a wide range from simple flat plate collectors to concentrating collectors to even PV heat pump type solutions in order to meet this process heat demand. And then finally, one of the bigger topics now for solar heat for industrial processes is the hybrid type solution. And I bring here an example of Rothaus, which is also a brewery in Germany. They have been doing a lot of solar energy work in the field, and they are now implementing a steam generation concentrating facility along with a PV or photovoltaic solution that has an electrical boiler attached. So you have this flexibility to provide renewable steam from two different sources to enable a higher solar fraction, but also a bit more reliability. So we'll be seeing these hybrid solutions more and more. Some may be combined with combined heat and power plant or heat pump and solar thermal, but all really driving to increase the largest amount of low carbon heat available to your industrial process. And please, if people have more interest in this topic, please take a look at the links below. A number of good resources here to expand your knowledge about solar heat for industrial processes and how you can get into the sector. And then finally, what is the future of solar heat for industrial processes? So the first is an expanded amount of applications. So there is a current task for the IEA Solar Heating and Cooling, Task 62, which is focused on industrial water and wastewater management. This is going to be a growing topic because not only do we need food, but we also need water, and the water quality throughout the world is certainly not improving. There are many places where water quality is quite poor, and this includes places that require desalination for drinking water. This is a big growth sector out there. Next up in the upper right-hand corner, we have a quite media-friendly company called Heliogen, which has been doing a lot of great work to develop a concentrating tower technology that provides low-cost, very high-temperature heat, upwards well over 500 degrees Celsius, which allows a lot of different processing like solar fuels, concrete, and metal refining, and they put out a lot of good work, and now they're trying to commercialize the technology to make large-scale projects readily available for zero carbon process heat and really that higher heat temperature level. And then finally, we have, well, one of the biggest labor drivers for the solar market is the cost of human labor to install these facilities. And a company called Sun Vapor over in California has been going through a lot of great work to develop a robotic alignment and assembly process for parabolic troughs out in the field to greatly increase the speed of which projects can be built, but also decrease the labor costs associated. So there's a lot of good work that's going on in the field, but the main focuses are to really get plants out there in the field and build as fast as possible, while also really tackling the other sectors that require higher heat or larger projects that require a lot of human labor to install the fields. So with that, I want to say thank you very much for your time today. My name is Dr. Stephen Meyers again. Please email me below if you have any interest to, but thanks again for this time.
Great. Thank you very much, Stephen. I was just about to interrupt you and tell you to speed up, then it was you were done just on the spot. Thank you very much. Very interesting presentation. Next speaker is Vassiliki Drosou. Vassiliki is head of the Solar Thermal Systems Department of the Greek Research Center for Renewable Energy Sources and Saving, CRES. She's also manager of the Solar Keymark Network, technical secretary of CEN TC312, Thermal Solar Systems and Components, and leader of the Sub-Task-D standardization and certification of the new IEA Task 64-4 Solar Process Heat, a joint task of solar heating and cooling and solar paces. And she's also board member of the Greek Solar Thermal Industry Association, EBHE. Vassiliki will tell us about the, well, very good progress or application of solar thermal siphon water heaters. Vassiliki, please.
Yes, indeed. Before that, I want to share my screen. So thank you very much, Andreas, and also thank you very much, Fred Bosch, for the great introduction. I would like also to welcome all here in participating in this session. I'm quite happy seeing such a high interest for the topic. We have already 199 people from all around from the world. I'm really proud to be here, and I wish also to thank Arabella and the Solar Energy Society for the organization of this conference of the Solar World Congress at 50. And as Andreas already mentioned, I wish to talk about the thermosiphon system technology. I will try to give in nine minutes the overview of this technology and also some inputs for opportunities and challenges so as to feed the Q&A session. So let's start by refreshing our memory about the thermosiphon system characteristics as a product. To the average consumer, okay, to the average consumer, just a minute, okay. To the average consumer, a thermosiphon system is a highly efficient product. We know that. It is very easy to be installed and also represents a very good value for money. Thermosiphon systems are decentralized systems. They offer independency from other users, a parameter that it is quite important in some countries like my country, Greece. Everybody wants to be isolated from other people. And also its procurement price is, in many countries is corresponding to an average salary, so we have a good value for money. Usually a system is replaced after 20 or 25 years, so we're talking about a product with long life. They need an eligible maintenance cost during their life, and they are considered safer than a conventional electric heater. After this, I want to discuss with you some overall facts in order to see what happened in worldwide level about the thermosiphon systems. It is true that worldwide, about 60% of all solar thermal systems installed are thermosiphon systems, and the rest are pumped systems. In this category of pump systems are included small, medium, large district heating systems, solar cooling systems. So it's quite a high percentage if we consider all thermosiphon systems and all the other pump systems in the other category. It is interesting to see that the newly installed systems in 2017 was 90%. 90% of the new installed systems were thermosiphon systems. This figure is quite lower for 2018. I'm going to give you later in discussion session some more information about this. Now, in general, the thermosiphon systems are more common in warm climates, such as South Africa, Southern Europe, or MENA countries, Israel, Jordan, Lebanon, Morocco, Palestinian territories, and Tunisia. Also, one important thing that I wish to mention is that China affects significantly the figures of installed capacity worldwide, as it holds approximately 70% of the newly installed systems, and also the approximately 70% of overall installed capacity worldwide. It is also a fact that in China, the majority of systems installed are evacuated tubes, but in the rest of the world, especially in Europe, the typical thermosiphon system comprised of flat plate collectors. In the same line, it is interesting to see also the distribution by type of system for the total installed glazed water collector capacity in operation. As I mentioned already, we see that approximately 60% of installed systems worldwide are thermosiphon systems, and we see the impressive figure in Latin America that 80% of thermosiphons of systems installed are thermosiphon. In Europe, this percentage is 40%, and in China, for the year 2018, is 60%. Okay. After this figure, I don't want to give you more numbers. In any case, all these figures and all these facts are included in the International Energy Agency Solar Heat Worldwide report that is provided every year. So if someone wants to have more figures, more numbers, it's easy to find them there. Now I want to let's say, to stimulate more the interest of the participants. I have here a comparison between a thermosiphon system and an electric car in terms of CO2 emissions avoided. Lately, a lot of discussions are on the table, and especially in Europe, and a series of supporting measures are considered for the support of electric cars. Now, if we consider the average emission of a new car, that is about 120 kilograms per kilometer, and an average distance of a typical car of 20,000 kilometers per year, then we calculate that the average CO2 emissions of an electric car is 1,400 kilograms annually. Or in other words, we can say that if an electric car would save all the emissions of a typical car, then, of course, this is not the case, then it would be saved the amount of 1,400 kilograms annually of CO2. Counterpart calculations for a typical thermosiphon system that is comprised of an area of flat plate collectors of 2.5 square meters and 150 liters, we could have the same calculations for CO2 emissions avoided, and we can see that this system, a thermosiphon system, can save 1,700 kilograms annually of CO2 emissions. So, from these calculations for this presentation, it is evident, and it is revealed the potential and the value of solar thermal systems, but also the need from policy measures in order to treat in fair mode the thermosiphon systems. Of course, the fair and robust policy measures is not only this the challenge that we have to consider for this sector. Something that is a lot of times is missing is the ability and the advantage that they have, the solar thermal systems, in terms of stored energy. the stored energy, this advantage that they have the solar thermal systems from medium, from low, medium, and high temperature for concentrated solar thermal systems. They offer the ability to help in the grid requirements, because they can be serve as a basis load. Now coming to the opportunities, the greatest opportunity for thermosiphons, specifically for thermosiphon systems, it is the highest priority in first energy saving measures and in building integrated solutions. As I mentioned already in my first slide, thermosiphon systems, they have a lot of advantages for this solution. They need the minimum interventions and the minimum changes for the integration in the buildings, and comparing to other solutions for energy saving like insulations or double glazing, they have comparatively the highest performance and the best value for money. It is true that the latest years, not really new products we have for thermosiphon solar systems, but always there is a room for improvements in the efficiency, in the reliability and durability, and so on. In the framework of International Energy Agency tasks, there was a task 39, if I well remember, a focus on the use of polymeric materials in order to produce an integral thermosiphon system or collectors from polymeric materials, in order to increase the durability and minimize the cost. Also, other innovations are transparent insulation or switching collectors for overheating prevention, for stagnation prevention, integrated collector storage systems. Some very impressive architectural designs are already in the market, or use of innovative storage materials also are in the market, as PCM, phase change materials, and so on. Now, apart from this, a very interesting challenge for thermosiphon systems focused on their digitalization and their integration in smart systems for houses. In this aspect, it is not only the advantage of using optimal the electrical and the thermal energy storage in the building, but also their characteristic to interact with electric and gas and heat grids as a demand side management. So this is really a challenge for thermosiphon systems, and also there is some research in a worldwide level in order to move in this direction. Now, last but not least, I want to mention the certification advantages for generally for thermosiphon, for solar thermal systems, and specifically for thermosiphon systems. The certification advantages mainly has to focus on the improvement of the quality and the durability of solar thermal system. The ultimate scope is to match the lifetime of a solar thermal system with the lifetime of the building. This is the ultimate scope that we have to focus on this. The most known, the dominant certification scheme for Europe is Solar Key Mark, but also other schemes that are worldwide, as SRCC in Australia, and or SAMSI for Arab countries. There are a series of benefits for manufacturers or for the consumers by using the certification, but the ultimate scope is to have in the market high quality products for the benefit of the consumer and for the benefit of the manufacturers and for the benefit of solar thermal. Now, this was from my part. Thank you very much for the invitation. I hope that you find my presentation interesting. Of course, I will be happy to discuss or to receive more questions, either directly in the Q&A session or directly in my email as shown here. Thank you very much for your attention. for the presence and the support in solar thermal technologies. Thank you very much.
Vassiliki, thank you for that great presentation. Now we heard solar thermal for industry by Stephen. We heard about thermosiphon water heaters from Vassiliki. And the next presentation will focus on large system, district heating and seasonal storage. It will be given by Jiao. He's Vice President and Chief Engineer of Solar East Holdings in China. He has nearly 20 years of experience in solar thermal utilization, product development and technology research with more than 30 invention patents. He's the Deputy Director of the National Solar Energy Standardization Technical Committee of China and participated in the formulation of more than 30 national solar energy standards. He also leads Subtask B of the IEA SHC Task 55. He's convener of the ISO TC 180 Working Group 3 and gold member of ISES. So I'm looking forward to your presentation, Qingtai.
Okay.
Floor is yours.
Okay, thanks for Andreas' introduction. I will sign my screen. Good morning and good afternoon, everyone. And I would like to share some information about what happens in Tibet of solar thermal, the solar district heating in Tibet from the first idea to implementance. And my presentation including 5 parts. The first is the background of the solar district heating in Tibet. Tibet is far from the mainland of China, and from the Lhasa, the capital of Tibet, to Beijing is around 3,500 kilometers. And the very special is in Tibet is average altitude is very, very high. Its average altitude is more than 4,000 meters, because the high altitude, so the temperature is very low. For southern Tibet, the average temperature is only 8 degrees, and even in northern Tibet, the average temperature whole year is less than 0 degrees. Actually, whole year need the space heating, but also because of the high altitude. In Tibet, there are no gas, no oil, no coal, and even no forests, but only very good sunshine. You could find, especially in winter, the solar radiation is even better than in summer. But before 2007, there are no any space heating. The only space heating source is coal down. And for some government offices, there are some very small electric radiator. So in 2007, the government built up a leading group of the heating and gas supply. And at the beginning, they decided to use electricity and solar energy for the space heating. But after several years operation, and they also do some project for the electricity and also solar systems. But they find for the electricity space heating, the operation cost is too high for the government. And for the solar space heating, because they at the beginning use the very cheap and very simple systems, so the system is not so reliable and bring the very bad reputation for the solar systems. So in 2012, the government decided to use the natural gas to supply the heating in Lhasa. But the problem of gas heating is also the high operation cost and also lack of gas. So at the end of 2015, the Tibet government had a conference for solar district heating to discuss the feasibility of the solar district heating. And in the middle of 2016, they completed the feasibility report of the solar district heating of Lancaster County. And at the end of the 2016, the feasibility report of the Lancaster project approved by the local government. and at the end of 2017, Solis won the bid of the Lancaster project, and at the end of 2018, the project put into operation and start to supply the heat to the Lancaster County. This is a completed project. This is a solar plant and the peat storage and the Lancaster County. And this is the project. The Lancaster is located at altitude is around 4,600 meters, and the solar collector is around 24,000 square meters, and peat storage is 15,000 cubic meters. And this is the first successful solar heating project in Tibet. The second is the design. I don't want to give more detail about technology. At the beginning, we invited the expert from China and Europe to do the problem analysis for the existing solar system, because there are near no existing system succeed to do to supply the space heating. So we invited the expert to do some analysis, and we find there are so many problems on the product, system design, construction, installation, and operation and maintenance. That is because the main manufacturer or supplier is in mainland China, but Tibet is far from the mainland. People in mainland know very limited about Tibet, and they usually use the experience in mainland in Tibet, so that is brings so many problems. This is the collector. For the collector, we do some research and calculation and simulation. After the calculation and simulation, at the end, we selected the large-scale flat plate collector to do the space heating. This is the systems for the Lancaster project. After the calculation, the heating season in Tibet is very long, 251 days, and outdoor temperature average in winter is -15, around -15. The designed solar fraction is 90, but actual solar fraction is 100%, and the supply and return temperature is around 35 and 60, 35 and 30, 65 and 35. And the solar collector, just as I mentioned, is 24,000 square meter, and the peat storage is 15,000 cubic meter. This is a system design with monitor simulate. We use the transits simulate the energy gain and the space of the price of the heat. So that the design principle is the heat price economic, and we also simulate the hydro balance solar plants. This is a design of the peat storage. This is the similar as that in Denmark, but there are some modify and improvement based on the condition of Tibet, such as we use the software and hardware combined layered technology for the indoor temperature stratification, and also the very special water treatment. This is a control unit. With the control unit, we totally integrated. That means we factory integrated design. We install and commissioning completely in factory. This is in order to reduce the installation time on site, and also we can keep the high quality. And we also use the irradiation control replace temperature control. And we also use the temperature compensations technology to supply the space heating to the network. This is some construction work with not only build up the solar plant, the peat storage, and the equipment room, and also the pipe and network, and in the radiator for end user. This is the peat storage. We know the peat storage is successful in Europe, especially in Denmark. But at the beginning, we don't know, we no confidence this technology or this also could be in Tibet because the high altitude and the very low temperature. But after the first snow in 2018, we have the confidence about this because the snow on the top of the peat storage is the same as side road. And they also measured all the data, including the solar radiation temperature, inlet outlet temperature, such as this is show the daily solar radiation and heat gain. The blue is the solar radiation, the red is the energy gain from the solar plant. And we calculate the average the solar efficiency of the solar plant. We can find the average solar efficiency around is more than 50%. Is higher than the systems in Europe and especially in Denmark. That is because in Tibet the solar radiation is very high in winter. And also we compare the measurement efficiency and the simulation efficiency. You could find the measured efficiency match the simulation efficiency curve very well. But in the morning, because there are so many cold circulation fluid in the solar plant, we need to preheat the fluid circulation flow. So there was the simulation is different. And also we measurement the energy in the peat storage. And the blue shows the total energy in the peat storage. And the red is the we call the high temperature energy. That means the temperature higher than the supply temperature. The green we call low temperature energy. This means the temperature is higher than the return temperature but lower than the supply temperature. This is system daily heat distribution. The yellow shows bar shows is the solar radiation. The red bar is the energy gain, and the blue bar is the energy we supply to the net space heating network, and the green is the energy storage we store in the peat storage. So you can find most of the day the energy gain, solar energy gain, is higher than the consumption of the space heating. So this is why the first year the solar fraction can reach 100%. We not calculate and measure the system ourselves. We also invited the third party to do the test. After 5 years test by the third party, it gives us the result nearly the same as our measurement. And the solar fraction is 100%, and the solar efficiency, average solar efficiency is around 50%. And also the very for this solar, because the high solar fraction, because the operation cost is very low, so the production cost in this for this project is the electricity cost is less than 2 RMB to heating area and heat per heating season. This is very special calculation. This is because this is China. We usually pay for the space heating. It's based on the heating area, the building area, and the heating season. And this is for this, with less than 2 RMB per heating area per square meter. We are running
a little late. Can you come to the end or speed up a little?
Okay. Thank you. Okay. So the inference for the biggest influence is for this project, we bring back the confidence of the solar district heating to government and the customer. And after that, we build up another more and more solar district heating project in Quebec. This is another project completed in 2019. The solar collector area is 35,000 square meters. The solar fraction is also 100%. This is the third project just put in use this year. This is a project Lhasa Vocational School. This project 10,000 square meter collector. And this is another solution. We install the collector on the top of the greenhouse and keep the space between collector row. And this we can keep the greenhouse not too hot in summer and not too cold in winter. And also we combine the solar and the air source heat pump. And for the biggest challenge for the large-scale solar district heating is the land for the solar collector. And this year we build up another demonstration project just in Häberle province. We install the collector 2.5 meters from the ground without affecting the use of the land. If this demonstration succeeds, the large-scale solar district heating have the huge potential market in mainland China. Okay, thank you for your attention.
Tsingtao, wow, very impressive. Large systems and a lot going on. Very successful projects. Thank you for that presentation. Let's move on. We're running late, but it's really interesting. Now we had heating with large systems. Next will be cooling. The speaker is Uli Jakob, Professor Dr. Uli Jakob. He's director of the Dr. Jakob Energy Research GmbH in Weinstadt, Germany. He holds a PhD in applied thermodynamics from the De Montfort University in Leicester, UK, and a diploma in building physics from the Stuttgart University of Applied Science in Germany. Uli has professional experience as an engineer and is a specialist for renewable energy systems and energy efficient buildings and industry processes. Since September 2012, he's the general manager of the Green Chiller Association for Sorption Cooling based in Berlin. And he has received a professorship from the Stuttgart University of Applied Sciences in June 2020 and was appointed the operating agent of the IEA SHC Task 65 on solar cooling for Sunbelt regions, which has just started. Uli, the floor is yours. Thank you.
Yeah, thanks, Andreas. Thanks for this nice introduction. So I will share my screen, just a second. So now we are switching from the use of solar heat for heating purposes to a different application, as Andreas was also already mentioning. So now we want to give you insight about another application in this solar business with the different technologies which are presented today. So we are looking now into solar cooling, which then be used for buildings and processes, of course. So I want to briefly explain you the situation of this kind of technology here in this Solar World Congress 50th anniversary, and give you an outlook where we want to go for, so that we can start the discussion later on, especially also, of course, on this application. So it's about the transforming, in that case now, of heat into cold or into cooling, air conditioning, however, depending on different application. Yeah, first of all, I want just to give you a brief insight what we are talking about, especially if you have a look on the future cooling demand, which is a different driver to that what you have already seen on the different heating markets. So from the ship applications now down to the large-scale district heating networks based on solar heat. So if you have a look on the latest IEA report from 2018 on the future of cooling, And if you have a look inside this nice report, then you can easily see that the energy needs for space cooling will triple between 2060 and 2050 about 3 times, which means especially for the residential sector, we have a huge increase of cooling demand through space cooling. And that's quite different, especially to the heating sector, where we have through the different energy measures in energy efficiency, heat insulation and so on, there we have more or less a drop of the demand. Again, in space cooling, it's quite different. There it's increasing, and that's the expectation next recent years with these high numbers here shown by this IA report. And moreover, and that's more important, especially if you are thinking about the use of solar heat and to convert it here in that case into cooling, is that especially in emerging economies like India, China, and others, of course, the need for cooling is more or less one of the major aspects in the near future, which they have to overcome by new ideas, by new technologies, and maybe there solar cooling can give a contribution. And especially if you look on the electrical provision by the different grids in this country, especially that space cooling will have a huge impact on the load side, and especially also if some of these grids then, especially in summer times, crash. So especially, of course, that you have just have this huge amount of split units, which then are running in summertime to cool down your spaces, and with that you have a great impact, which maybe can be somehow served by solar cooling systems to have a portion on that increasing cooling demand within the next years. So the question now is, if you have this insight now, first of all, what the cooling market will look like in the next years, what probably can solar cooling serve in that way to somehow have a stack in this market. And again, solar cooling is not a single technology in that way to have another application for the use of solar heat. No, usually it's a portion, it's a part of an overall system. So still domestic hot water, or in processes in industry, there we have also solar process heat and cooling usually beside. So it's not a standalone solution. It's usually combined, so use of heating or solar vapor and cooling at the end. So what have we achieved so far? We did a study in 2015, which was presented during the ISES conference in Istanbul in Turkey at that time. And we have collected data all over the world from installed solar thermal cooling installations. And you can see here on the world map, depending on the different colors, from blue with a low density to green with a high density, where you can find already solar thermal cooling systems. And maybe this world map is not the complete picture, so maybe we have missed some installations, of course, but that's what we have found at that time. And what you can see here is especially that in Europe, we have a lot of installations, we have a lot of experience there, but also if you go to Southeast Asia, so India, China, and so on, and other countries, and back to the US on the other side of the world. So there's quite a bunch of experience already available, and you have not to forget that this kind of technology, so the use of solar heat to be converted into cooling, is now more or less 150 years old. But still, and that's the major aspect here, it's still a niche market. So we're talking about 1,800 systems installed worldwide as a summed up number. So it's really not that much if you compare that, especially with the annual sales numbers of the so-called split units. So these small air conditioning units up to 2 or 5 kilowatt cooling capacity. There we are talking about 130 million units sold each year at present. And this number is rising year by year. So that's the market. So we're talking about 130 million potential solar cooling systems. And as you can see, we have already installed 1,800. So it's just more or less nothing in this portion of the cooling market. But there's the room for improvement, of course, and that's why we are also looking in that technology from an IEA perspective in the new task 65 on solar cooling, which was mentioned before also by Andreas in the introduction. Now, what's the outlook? And that's what I want to discuss with you later on, so you get an insight what a cooling market is going for. You know now somehow where we stand, what is our current status in this solar cooling developments and markets. And from our perspective, the future growth, of course, will be stimulated, of course, by future technical and economical improvements. So the focus, of course, on the technical side is to innovate more affordable, safe, and reliable solar cooling systems. So, but that's more or less a technical wish and something which we have to overcome for all of the solar thermal technologies. And there we have, of course, different positions today. Again, especially for solar space cooling, it's that we should focus first of all on energy conservation on the buildings, and then the use of these kind of renewables, in our case now solar thermal heat. And of course, from a technical aspect as well, economic aspect, it's also important that if the electricity costs are rising, then especially those kind of technologies here, solar cooling systems, have a more economical, interesting feature than the conventional systems. And that's also something which is you should take into account. So just to give you an idea, we did a study some years ago for the R3, so one of the UNIDO GenSec Center for the Arabian states. And there we figured out that already of these 22 states, that in about 7 to 15 states, again, today, solar thermal systems and also PV cooling systems are feasible also from an economical point of view over a lifetime of 20 years. Again, the existing grid costs and the reference system of split units. So there are already places, countries where solar thermal cooling already makes sense today. One stimulating aspect to get more systems in place is also, for example, for European perspective, the F-gas regulation, that you are not allowed to use any kind of refrigerants in the future which are not natural, which means at the end that you have to use water, ammonia, butane, and so on to use as a fluid inside your machines, either heat pumps or chillers. And another aspect, also from a technical point of view, of course, is to stimulate this push as standards for absorption chillers. We have now 2 standards here in Germany. The latest one is from the VDMIA, which was recently published, number 24247, and this is just published 1 month ago. And this maybe helps, as Vassiliki was saying, also for the thermosiphon systems, that such certification schemes are quite important to get these technologies in place. But moreover, it's much more important, especially also for solar cooling, but I think it's general also for the other technologies, but for solar cooling especially, that we have to create trust in these technologies. And we need more political advice, which means for the trust, we need online databases on these systems. So we have seen also for this nice presentation before from the Chinese colleague with the installations in China on solar district heating. Those are the projects which we have to show to the community, to the stakeholders, and especially then if you're coming back to the political issues, we need policy advice for energy policy decision makers, that they know what information should they probably use to stimulate this kind of technologies, to push it forward, and also road mapping. So policy advice, road mapping is from my point of view, and that's what I want to discuss further on in the next minutes in this session here with you, how to overcome this barrier for the widespread of solar cooling technologies. And with that, I want to end my presentation and to leave some time for discussion later on. So
Thank
thanks
you,
for your
good presentation. Thank you. potential for solar in cooling. We are all aware of that. Question is how to get there. Now we're done with the presentations except the recorded one from Maria. Maria Wall. Maria, oh, thank you, Arabella, for introducing this slide. I will read it out. Maria is an associate professor at the Division of Energy and Building Design at Lund University in Sweden. She has a master in architecture and a PhD in engineering. Her research has included different issues related to energy efficient buildings and solar energy strategies. She's at present leader of the research project, the ISHC Task 63, which recently started on solar neighborhood planning, including both passive and active solar energy strategies. She was the main initiator and developer and is also the director of the 2 years master program in energy efficient and environmental building design at Lund University. So Maria, I'm very much looking forward to your presentation on the integration of solar technologies in building.
Just 1 second, we are gonna have a recorded presentation from Maria and it should be coming up on your screens now. And
so I will talk about solar neighborhood planning. Looking back, solar energy has been important for buildings and urban areas for a very long time. And as early as 400 before Christ, the ancient Greeks began orienting their houses to gain the most of the sun during the winter months. And for more than 2000 years now, urban density was then ruled by access to daylight and natural ventilation. And a few important terms are solar access, which is the ability to have uninterrupted direct rays of sunlight fall onto one's property. And another term is the right to light, which is a legally enforceable right to a reasonable proportion of the natural unobstructed flow of direct solar radiation. And this for now 2000 years, and then came electricity with electric lighting and mechanical ventilation in the 20th century. And then the simple rules to plan a city were forgotten or not needed anymore. So, and we got the densification of cities. But now we are in a way going back to this right to light, because we have sustainable cities and renewable energy that push for this right to light to get daylight and solar energy production. Of course, we have a problem that we have an increased population growth and environmental gains of walkable and public transport that push towards increased density of cities. So it's not really, it's not so easy to be an urban planner. The solar contributions we have today and use today, more or less, are of course, as earlier times, passive solar energy for indoors and outdoors to reduce heating demand and to improve thermal comfort and health. We also use daylighting for buildings and outdoor areas, which reduce electricity for lighting, and it also improves visual comfort and health. We also use local and renewable energy production with photovoltaics and solar thermal systems. And this could help to create energy self-sufficient environments, to not rely on energy imports, and to create resilience to energy price fluctuations. Further, we can use solar for local food production and the use of green areas to improve the air quality and reducing stormwater. So we can really use solar for many things. Coming to the opportunities, It could be a means with solar neighborhoods could be a means to achieve net zero energy districts and low carbon cities. When also addressing both solar energy production and daylighting and passive solar when we plan neighborhoods. This enables us to identify synergies and to avoid conflicts between the competing uses. So this is very important to do in an early planning stage. And we should also have a clever use of available surfaces in the city and the neighborhood. We can do a lot there. Another opportunity is to create long-term solar access. For instance, if you invest in PV panels on your house to produce electricity, solar electricity, you don't want your neighbor to erect a building that is shading your panels in maybe 1 or 2 years later and making them useless. You want to be sure that you have solar access for a long time. So this is a very important aspect. So what should we do then? I started a to-do list, and this of course includes in a way connections to challenges. And the first thing I put on the list was that there is a need for legal reform in many countries regarding solar access protection and improved planning approval processes where we can have informed decisions made. This is important. We also need to develop and test different concepts for neighborhoods and the role of solar in these. Further, we need to develop strategies and methods how to plan for better use of surfaces. This is really an unexploited asset we have in cities. We also need to develop tools further for analysis and not primarily adding new tools, but improve and guide which tools to use, when and by whom. And especially the developments are on connecting tools and to create clear and efficient workflows. And also on studying of multi-criteria analysis on the neighborhood scale and not only on single buildings. Economic values are important, of course, and I would like to highlight also added values. For instance, energy security, reduced greenhouse gas emissions, and so on. And how to develop methods, how to evaluate such important factors, and to not only take into account direct costs. Knowledge transfer is always needed, and it could be between academia and the building sector or within. I also noted here acceptance, and I was thinking about buildings that will get larger and larger areas covered with solar panels. And to get building permits and acceptance, solar thermal and PV products need to continue being developed, also for architectural integration, and not only focused on technical performance. Because if they are ugly, the risk of not getting installed is large. And then it doesn't matter if the product has a high efficiency or not. So this is a few examples. I stop here.
So thank you very much. Now, we ran a little late. It was very interesting and very nice presentations. If you agree, I suggest we extend a little by 10 minutes or so we do have some time for the Q&A. And I suggest we start in the order of the presentations. And I will select and read out one question to each of the presenters, and we start with Stephen Meyers on the process heat, industrial heat solar heat for industrial processes. Let me read out a question. Where are we? Can you give me your opinion, especially for low temperature solar thermal applications for process industries in comparison with heat pump application? Since heat pump development claiming to support low temperature applications in industry as well. And I know that was a topic you were working on during your time in Kassel. What is your view on solar thermal versus heat pump for industry?
Sure, thank you for the question. It's quite relevant, and it's still being discussed because it really depends on the conditions. So what you do have is you have a very low carbon source with a decent efficiency, and then you have a heat pump that uses grid electricity or maybe electricity from a PV panel. And if we speak about the efficiency side, let's say a solar thermal panel for lower temperature, maybe 50–60% efficient over the year, whereas a PV panel is on average 15% efficient, converting sunlight to electricity. But now you have a heat pump that may have a COP of 3 to 4, so you multiply that by 15, and then you're back at the efficiency standpoint. So it's from a sheer solar to thermal energy gain, it is quite similar. So then you really have to get down to a cost comparison, and that is a bit at price parity right now, depending on your location. So it really is application specific in your area. What I will say, which was a major conclusion from my dissertation, was if you're comparing solar thermal with a grid-powered heat pump, if you're able to operate your heat pump over 3–4,000 hours per year, then the heat pump is generally a better way to go. But if you can, if you can only operate it really 1–2,000 hours a year or less, then solar thermal tends to be a better option. But there are a lot of boundary conditions that really affect this comparison. So I really offer you to go read my dissertation for a really good methodology and simple tool to compare the two options. Thank you.
Okay. So thank you, Steve. So it's really down to the economic justification, not the technology. You can't say, okay. So thank you, Steve. Next question will be to Vassiliki on the thermosiphon systems. There was, let me read out or check it. Why the fall in the thermosiphon percentage was the question. And in other words, you referred that in 2018 there was a low percentage of newly installed system compared to 2 or 3 years earlier. And what is the reason behind?
Yes, this is, as I mentioned, thank you for this question, first of all. This is mainly to the major play in thermosiphon systems. As I mentioned, this is China. And also, as I mentioned, China holds approximately the 70% of the newly installed systems, and also the total installed systems in operation. So, as already mentioned by Mr. Jiao, China moved to large district solar heating systems. So this means that a great part of the installed collectors now are not thermosiphon systems, are pump systems. Just to mention that during 2019, if I will remember 47 systems they have already installed with an area of more than 300,000 square meters. Just one district heating system holds more than 35,000 square meters of flat plate collector. So this is the main reason of changing the balance of thermosiphon systems and pump systems.
Okay, I got it. So it's, thank you, Vassiliki. So it's not that the thermosiphons are not as good or have a decline. It is the rise of large systems that move
the different balance. Yes, exactly. Yes. In any case, everything is solar thermal, so we're a big family. They're very welcome. The total installed square meters are increasing, so this is good. In any
total
case.
installed rises,
Yes,
and
yes,
still
yes.
we are very much in favor of the thermal siphon systems for as water heaters, where the space heating is not such much of an issue. That's the.
Of course, we start from the simplest version of thermal siphon system up to concentrated solar thermal systems. All belong to the same family, so we're happy with this situation. Thank you very much.
Thank you, Vassiliki. Come to Tinta. You showed these really impressive pictures and new big projects. And what was mentioned is the high solar share, 100% solar share. So you do all heating with the big solar field over the year. And the question here is actually it's one small question and another one attached. Does this also cover all the hot water demand? And second, coming the 100% solar share, comparing to other countries, especially Denmark, which is one of the forerunners in solar district heating, there the solar share is lower. So it's typically a hybrid system. So typically, I don't know, 40% with a pit storage or 50 or so. Why is that? And how? What is your estimation of the high solar share, where everybody else would say, well, that's not probably the cost optimum, or yeah, what is your estimation?
Two questions. The first question is, this system is not including the hot water supply. This is because the Chinese situation. The Chinese situation is the space heating is separate from the hot water supply. Even in some big cities, the space heating is only for the space heating, not for hot water. This is the first question. The second, the high solar fraction, that is not the because the technology or something, mainly it's because of the policy. That is because in Tibet is a very special location in China. So usually this large projects or public project invest by the central government or other province from mainland, but the operation costs should be paid by the local government. So local government needs the high solar fraction, but the local operation cost. So this is and also another reason is the very high solar radiation. Average solar radiation is more than 1,000 watts per square meter, even in winter.
Right.
Okay.
Right. So in the end, regulation is the driver, but behind that is also an economic estimation, because you want to have low operational costs at the local government. Very interesting. Okay. And so I find it really encouraging, because in the end we want 100% decarbonization, right? And this is it shows we can do it. We can do it with solar thermal heating. We can get to 100% solar share, 100% decarbonization. Very good, thank you. So that was the question on the district heating part. I've come to the cooling and read out the question here. Where is it? So actually, it's also again two questions. One short one, and then another one that you will not be surprised about. The first one is on your map. You showed the blue and green, and Alaska was also green. The question was, does Alaska need cooling? And the follow-up question is then your view of solar thermal cooling versus PV-driven chillers. So what is the role of the solar thermal, and your estimation on the future part here? Uli, please.
All right. So thanks for Andreas. Yeah, first of all, coming back to Alaska, as Alaska is part of the US, and we have colored the countries in this study with the solar cooling system. So that's why Alaska is also somehow colored. But at the end, cooling is also needed in Alaska. I was there 1.5 years ago, and you find there are a lot of fridges and other stuff also in processes where cooling is needed, where solar cooling, PV cooling, or either solar thermal cooling can also play a role. So Alaska is still a place where cooling needs are there. So that's one thing. Coming back now, as I already mentioned, PV cooling, solar thermal cooling. There's of course two kinds of technologies where you can use solar irradiation to be converted into cold. And as the question was asking, where are the markets, especially for PV cooling? So there are markets, especially from our point of view, for small systems, which means between 2 to 5, 10 kilowatt cooling capacity. We do not see it for large systems where we are talking about 1 megawatt or more. There we still see the solar thermal cooling systems, especially because of the energy management by storages. So PV cooling probably will play a role in the small systems, but as we have done a lot of different surveys all over the world, probably there are some installations, but there are no companies really pushing that. And there were some companies in the past in Europe trying to push PV cooling, especially in France. They have all give up already after 2 to 3 years. So those companies which were trying this kind of technology to bring that as a system on the market not succeed so far. So I hope in the future there will be a version also for PV cooling. But what is more interesting and what I want to probably summarize in that way is that we also should look into hybrid systems here in solar cooling, because that's the new kind of technologies which are popping up now. A combination of a compressor chiller with an app or adsorption chiller in one system, usually also in one shell already, where you can use PV and solar thermal as an input to run such systems at a very high efficiency, which you can achieve EERs, so energy efficiency ratios, above 8 to 10 for the overall system, especially in hot climates. And that's really an improvement from a technical point of view, where we can use renewables to somehow also improve the already existing compressor technologies through this kind of combination.
Okay, very interesting. Thank you, Uli. Now, I would assume that these combined systems are rather large systems, aren't they?
You can only buy such systems from European manufacturers starting at about 5 kilowatt cooling capacity. With these hybrid systems, there are many European funded Horizon 2020 projects where you can already gather data, so from monitoring data from different institutes. So this kind of systems, hybrid systems, are now in the market since 3 to 4 years. As I said, also in this with this support through research projects to get real measurement data, to get trust in this kind of technologies. So, and systems which you can buy in the hybrid market so far are then up to 150 to 200 kilowatts. So that's what different manufacturers are supplying to the market. So between 2 to 5 up to 200 kilowatt as a hybrid system.
Very cool. Thank you, Uli. I think then we would close here with the Q&A. I think it was a really very interesting session. I would love to continue discussions. Now we see the final screen. Thank you. And I thank again Maria, Steven, Vassiliki, Tingtai, Uli for the presentations, and would like to hand over again to Fred. You're still around. It's very late for you, for some final words.
Well, you know, since I was involved with IEA Task 1, 2, 3, 4, it's quite exciting to hear about the 60s. I would also like to thank all of the speakers. I think the presentations were excellent, a lot of progress. I especially like the last comments about hybrid, because in the other sessions of this conference, you just see hybrid is happening. It's the integration of technologies, PV and thermal, for example. And Andreas, I'd like to thank you for your moderating, which showed its strength in the end with the Q&A, and your interactions with the speakers, which elaborated on the answers. I thought that was very good. I'd like to ask people to check for follow-up messages from ISES on upcoming activities. And now I'd like to make a pitch for money. This was a zero registration conference, but there was a lot of cost to put it together and to put the booklet together in the museum. So if you wish to make a voluntary contribution, please do. And with that, I would like to thank you and close this session and try to get to sleep without my wife catching me. Thank you, everyone, and good morning, good night, good day.